Okay, so we are ready for the last talk of this day. It will be presented by David Nadler of University of California at Berkeley. He's a Sloan Fellow and he's a Fellow of the American Mathematical Society. And this year he received the Frontier of Basic Science Award. And next year he'll be an invited speaker at the International Congress of Mathematicians. So please, David, the floor is yours.
Thank you. The mic is on? Yeah, oh, great, okay. Yeah, thank you, Helga, and thank you to the organizers. I guess as the last talk of the day, I'd like to invite us all to thank the amazing organizers. It's been really a wonderful week so far. I know the activities will continue, but in any case, thank you to the locals who have really made this a special experience. So, before I get started, I wanted to, Katrina's made a comment during her talk that reminded me of an anecdote I wanted to tell. So she mentioned that spending time with Masaki involved two things. I think you put them in the order of great dinners and great mathematics. Okay, anyway, so in some order, great dinners and great mathematics. And so I'd like to just briefly tell the anecdote of when I guess I first met Masaki and first went to Kyoto. And I was a postdoc, and I went along with Kari Vilonen, who I understand is not here celebrating because he's in Kyoto right now visiting. I'm not sure how that happened, but in any case, Kari and I went to Kyoto together. And Masaki said, I will take you out to dinner tonight, and we'll go to, it's a kind of seafood restaurant. And it's not, Kari said to me, it's not really a seafood restaurant. It's kind of more like a small bar. Maybe it's not there anymore. I don't know. It's like a small bar. And Kari said to me, this will be the best meal of your life as long as they don't bring the giant clam. So we go to the small bar, and when we go in, it's packed with people drinking. Some are eating too, but mostly people are drinking. And, Masaki walks in, and it's Kashiwara sensei, and please come with us. And we went upstairs to, I guess, the chef or the family's home, where, and they have the table set out, and the three of us sit down, and it's, we're ready. It's going to be an amazing experience. I have already given you the punchline, but it's going to be, we're sitting in their home. They're about to serve us this amazing meal, and Kari looks at me, and he's like, it's going to be fine. And then, of course, the first thing they bring out is this clam that is, this big. And the meal was an amazing, amazing meal. I noticed Kari never ate the clam, but I did. And it was, it was a wonderful meal and a sign of Masaki's hospitality, which made a great impression on me. I was just a postdoc, but he, from the start, was always incredibly welcoming and, really treated me with all the respect. So anyway, this was a kind of start to a very important relationship for me personally and mathematically. So what I'm going to try to do in my talk, so I should say I was asked as the last speaker to give a talk that's a bit of a wrapping up. I don't know if that's accurate or exactly the way it was phrased, but my talk will attempt to be less technical. I don't know. I don't know if I have any equations or turtles or anything, or cranes on my slides, but we'll see. In any case, I'm going to try to tell a story that, of course, doesn't cover all of Masaki's mathematics. That's impossible. We've already heard about so much. So some of what I say will overlap with things we've heard of before, but what I'd really like to do is to, in some sense, go beyond Masaki's work to work that he's really influenced. Okay, so we've heard a lot about work he's done, and also work that he's directly involved in its furtherance, but there are huge areas of mathematics right now that are essentially built on his ideas, and I'd like to pick one of them, which is what you might call microlocal geometry, and kind of explain some aspects of it that are really important in current developments. Okay, so just to highlight, the theme of the talk is to kind of spend a bit of time with this word microlocal, and this is just a pun, that the global influence of this microlocal perspective. Okay, so to get started, before we can go microlocal, we need to understand local, and local versus global. And already this is a theme, this idea of what is local geometry is a theme that was already appearing in the first day of this week when some of us met with competition winners, the young talents, and Masaki presented and was asked something like, what is your favorite field of mathematics? And he spoke about how he started in analysis and moved through geometry and is now in algebra. But there was a theme that he presented that algebra is really this amazing language to describe geometry. So I'd like to just kind of start there with just noting that what I think is a good working understanding of what is local geometry is that's the geometry that we can really describe via algebra. So as soon as I write Q1 through Qn, I think everyone in the room now has some sense of what we're talking about. Maybe we're talking about complex n space or real n space, but we're talking about something that I think we all have a sense of. Also on this slide is a major step in mathematics, which was the idea that we should treat not just position, but momentum on the same footing. Okay, so thanks to Newtonian mechanics, we understand that it's very useful to introduce momentum coordinates to help us separate variables and solve Newton's equations. But the idea that momentum and position are on the same footing is an incredibly important one, which is really the theme of microlocal geometry. Okay, so from the very start, I'd like to kind of introduce this idea that we really don't think just of position, we think of position and momentum at the same time. Okay, and I'm very happy to be interrupted during the talk with questions. Okay, so before we go from local to microlocal, let's go back up to global, and let's ask what is global geometry, and this is something that I think mathematicians are still wrestling with. It's extremely hard to understand or to kind of know how to study and how to think about global geometry. So one starting point for global geometry is Riemann with the idea of a manifold, and that will be the type of global geometry that we'll think about during this talk. That's what Andrea described as curved spaces. And I don't speak German, but I hope maybe, anyway, I don't even dare to try to pronounce manifoldness. But here already we see something that we already saw in Andrea's talk, which is that a function like the square root, nth root of a coordinate doesn't make sense except locally. So if we want to speak about it globally, we need to introduce a new space, a kind of helix living over our usual space. And this new space is what a manifold is. In fact, Riemann organized manifolds out of saying that they were collections of all the spaces you could get above your space, thinking about coordinates and patching them. Okay, so when we go from position to position and momentum, we're then in the realm of symplectic geometry, which was first seriously studied as a subject with symmetries. I guess another theme of this week is that you don't really know what kind of mathematics you do until you study what symmetries it has. And the first person to really seriously study symmetries of symplectic structures was Lie. And so one theme is that we start thinking locally or globally about manifolds or coordinates, and we always want to keep position in the game. It's a kind of, I don't know, philosophy I've been told is to correct the kind of mistakes of science. So it was a mistake of science to somehow drop momentum or to not include momentum from the start. We should always include momentum from the start. And from that point of view, we should really think that we have a symplectic manifold, not just a manifold. Okay? So our orientation will be towards thinking of position and momentum always at the same time. Okay, so I learned something preparing these slides. So I had remembered that the word symplectic was coined by Hermann Weyl. I don't know whether it's useful. I'll read the quote. Of course, you can read it. But the name complex group, formerly advocated by me, in allusion to line complexes, so that was the old name, as these are defined by the vanishing of antisymmetric bilinear forms, has become more and more embarrassing through collision with the word complex in the connotation of complex number. I therefore propose to replace it by the corresponding Greek adjective symplectic. So I learned two things. I learned that a calc is where you do this kind of replacement by language. So symplectic is the Greek word. But the other thing I learned is that Dixon, who was the University of Chicago's first PhD and a leading figure in American mathematics, had called the symplectic group the abelian linear group. So, which would be incredibly confusing. If Weil thought that complex group was confusing, you can imagine if we all called it the abelian linear group, that would be extraordinarily confusing. But in any case, I was kind of amazed and pleased to see that Abel had, made some serious first forays into symplectic geometry. I mean, kind of remarkably. I had no idea. Okay, so this is maybe just a side point, but in any case, a pleasure to recognize an achievement of Abel that I think is not kind of commonly spoken of. Okay, so now I should say the way that my talk is organized is we'll have a kind of brief ramping up, and then I'll eventually get to some of Masaki's contributions and then talk about what's beyond them. Okay, so we're still very much in the ramping up. Okay, so what's the bridge between local and global? Before we can go microlocal, let's understand the bridge between local and global. And this is, for this talk, this will be sheaf theory. Okay, so we saw a bit of sheaf theory in Andrea's talk. The key motivation for sheaf theory was this idea that we might be able to solve a differential equation locally, but as we propagate the solution and continue it, we may arrive back at a different solution. Okay, locally, the solution was unambiguous, but as we come around, we may come back to a different solution. And the way such things behave mathematically is organized into the notion of a sheaf, which I'll remind you of in a slide or two. There's some sort of overlap with Andrea's talk, which I think is unavoidable. I don't think if I just said, I'll refer you to the past talk, that would be a good tack. In any case, Laureate, a French mathematician, was the first, or traditionally credited to being the first to formulate what a sheaf is. So I think that's a kind of important recognition of Laureate. Okay, so I'll take Gelfand's tact that before you give a definition, you should give an example. So the definition is then obvious once you kind of understand the example. So what is a sheaf? So first an example of what is a sheaf, and the next slide will be a definition of what is a sheaf. Okay, so here is, it turns out, not by planning, but the same equation maybe in a different form that Andrea had in his talk. So this is a kind of differential equation for on the punctured complex line. And locally, it has solutions that all look like constants times z to the 1 over n. But of course, z to the 1 over n is ambiguous. As you come around, there will be some monodromy. So if you live, I don't know, to mix metaphors, if you're a turtle living in a small part of the punctured plane, it looks just like you're studying some kind of constant functions, but with a symbol z to the 1 over n next to them. But as you come around, they behave slightly differently. They twist, okay? So the behavior of this gadget, this f sub n, so when n is 1, then this is just the constant sheaf of locally constant functions. But when n is not equal to 1, this is some kind of twisted version that you only sense when you ask global questions about it. If you ask only local questions, you can't really tell the difference. Okay? So this is the gold standard, for a sheaf, and the definition of a sheaf is just intended to formalize this. Okay. So one of the amazing things about sheaves, as with categories, is that they're of ubiquitous application. So on this prior slide, I tell you that the basic example of a sheaf is the sheaf of solutions to a differential equation. And then the first thing that I realized, I don't know, maybe it's a bit jarring. The first thing you see on this slide is Meyer-Vietoris gluing from algebraic topology. Okay, so it just turns out that this notion of accessing global geometry by gluing together local geometry is, of course, a ubiquitous one. You'll find it in analysis. You'll find it in topology. In any case, I just wanted to, once and for all, I have very little technical mathematics in this presentation, but I wanted to at least give one of the fundamental definitions, because a lot of what we're going to kind of discuss is Masaki's contributions to the theory of sheaves. Okay, so what is a sheaf? So it is a functor in a modern language from the category of open sets, So what that means in kind of down-to-earth terms is to every open set, you say get a vector space over your fixed field K, and then if you have an inclusion of open sets, you get a restriction map. So you're trying to model exactly what happens if you were to look at solutions to a differential equation and you could restrict them to a smaller domain. Okay, and then the key property, which is formulated in a technical-looking way, is just to say that a section, so a section over an open U, is just a collection of sections that agree on the overlaps. Okay, so this is kind of the key slogan for all of sheaf theory. And this was kind of first formalized by Leray. Okay, so a lot of what we're going to talk about is Masaki's kind of impact on the theory of sheaves, and so I wanted to just at least be all on the same page with what I meant by a sheaf. Questions, comments? Okay. So let me tell you an early example of the theme or the power of sheaves, and this is one that, well, we'll talk more about Masaki's work in a little while, but this is one that many people learned first from his writings, and this is Cartan's proof of de Rham's theorem. Okay, so de Rham's theorem, I'm going to give you a, I don't know, you're maybe already reading it, a 1.5 line proof of de Rham's theorem. Okay, so this is a kind of very beautiful idea. Okay, so de Rham's theorem says that the de Rham complex of differential forms with the de Rham differential, so that complex calculates the singular cohomology of your manifold. Okay? And the modern proof, or a modern proof using sheaf theory, maybe it's not so modern anymore, I don't know, the proof is about 78 years old, is that, well, there's a natural map, okay, there's integration map from differential forms to singular cochains, and then you can check that both of these complexes satisfy the kind of gluing that sheaves satisfy, okay? And then you prove for each of them a Poincare lemma, which says once you know that they're sheaves, all you need to do is check that they're doing the same thing locally. I mean, once you have a map between two sheaves, if they're the same locally, then just by formal patching, they're going to be the same globally, okay? So this is a kind of very beautiful proof that, I don't know, I've experimented with teaching this kind of proof, or using sheaves in a first course in algebraic topology with mixed success. But anyway, I think it's worth trying. Okay, so this is one of the first moments where I think you can see the power of sheaf theory, that you really kind of see this statement not as some kind of sophisticated geometric statement. It's a kind of formal statement about these objects. Okay, so this is a kind of stepping stone to where we're going. Some important moments in the development of this idea of sheaf theory as an interplay between global and local. So one can't give a talk with words like microlocal or otherwise in them and not talk about Sato. So Sato, as we've heard, introduced algebraic analysis, and two of the kind of signpost achievements are the idea of, well, one of them is the hyperfunctions, and other elaborations, we'll talk more about microlocal things, but one of them is hyperfunctions and other solution spaces, and the key idea is that these are not objects of analysis, but they're really accessible just through kind of algebraic operations with sheaves, okay? So once you kind of really understand sheaf theory and what you can do with sheaf theory, you can access all sorts of amazing aspects of analysis without doing much analysis. Okay, so that's kind of one that's kind of the introduction of the subject that we're all now discussing today. And then the other is, as Andrea mentioned, is this, I guess, Katata conference, where Kashiwara, Kawai, Sato's paper was under development, as I understand it. I don't know, the paper was published years later, or, well, anyway, but it was under development, and here was where really the first definitive results in microlocal analysis, the idea that we should really understand linear partial differential equations, not just by thinking about them locally in position space, but thinking about them microlocally, thinking about them both locally in position and momentum space. And we're going to spend much more time on this idea, but I just want to flag this as really the kind of starting point or the first definitive plateau in this subject. Okay. I realize maybe this is the first picture of Masaki, and there will be others, and I noticed the hair grows at the hair is different lengths during different phases of mathematics. I'm not sure if there's a correlation, but anyway. Okay, so just a slide, this was really the content or the subject of Andrea's talk, was the idea of the Riemann-Hilbert correspondence as a kind of culmination of this theme. Okay, so the idea that algebraic analysis and sheaves were the right language to understand all sorts of phenomena really reached its culmination with Masaki's Riemann-Hilbert correspondence. So I'm not going to kind of belabor, I don't know if belabor is the right word, I'm not going to kind of repeat what we've already heard, but maybe just, just mention sort of, I kind of went too fast, just mention what Andrea said, which is that, well, there's a kind of, maybe you used the word derived at some point, there's a derived equivalence between regular holonomic systems of differential equations and their complex constructible sheaves of solutions, and within this is a more fundamental abelian equivalence between regular holonomic systems and perverse sheaves of solutions. Okay, so this is not the subject of this talk, but it's impossible not to kind of flag this as a seminal moment in the subject. Okay, so we're going to get to microlocal sheaves. We're still in the preamble of the talk. I should say that I always have two fears giving a talk. One is that I will have way too much material, and I will need, I won't keep you, but that I'll still be here 15 minutes after the talk is ending. And the other is that I have way too little material. So anyway, we'll see. I'm not sure where we're at today. But I do want to, this is still preamble, so I do want to mention that independently of microlocal considerations, sheaf theory in Masaki's hands really became the central tool in geometric representation theory and continues to be the central tool. We'll see that. So if you're a student who's interested in geometric representation theory, I think learning about cohomology and sheaves is as good as anything else you could be interested in. It's really the language that organizes so much. So maybe I just mention some real high points of the subject. So we've heard about some of these in other talks. So there was Masaki's proof with Brzezinski of the Kazhdan-Lustig conjecture. Okay, so my talk is not about these topics, so I think I'll just go through them as just just for you to remember later. I want to mention Hata Kashiwara specifically because we'll see later. This was a paper in which Masaki and Hata really explained how to think about Springer theory and character sheaves in terms of differential equations that Harish Chandra really studied and would recognize. Okay, so really, people have said Masaki is a bridge. This is really a bridge between a kind of the founding of modern representation theory in the hands of Harish Chandra and the way we think about it now with all sorts of beautiful combinatorics and classification theorems. So this paper is a kind of real seminal moment. And then I also want to mention Kashiwara-Schmidt's collaboration, which I don't know if this reference is the correct date, but in any case, all of the geometry of geometry and representation theory of real groups is now seen through Masaki's work with Schmidt on thinking about representations in terms of sheaves on flag varieties. So a kind of parallel topological point of view to Balance and Bernstein's algebraic localization. So kind of another amazing achievement. Okay, so the last preamble slide is kind of a fast forward to today, or really it's remarkable, a fast forward to 1990, okay? So it's rare that, I think it's rare that a text is written and 35 years later, it's not only still the foundational text, but it's also still the text you look at for kind of research directions. So this is an amazing book. Here's Kashiwara and Schapira in Italy, 2009, and here's their text, which was published first in 1990. And yeah, I think it's hard to, as Schapira said in his in the short video we saw. What did he say? I think we did something important. Okay, so this is true. Okay, so this text, much of what I'm going to tell you is an outgrowth, the mathematics that have grown out of ideas that are in this text. And something that, like I said, still shocks me is this text is not like just an educational text, nor is it just a research text. It's somehow two things are happening simultaneously in an amazing way. Okay, so that's it for the preamble. Okay, great. So now I want to kind of turn to the main subject of the talk, which is microlocal sheaf theory. Okay, so we have now arrived at the main subject of this talk. So we've gotten here by maybe viewing sheaves as solutions, as naturally arising by considering solutions to differential equations. And then one can ask, well, what does the microlocal analysis that we saw in Sato, Kashiwara, Kawai's work and subsequent work, what does it mean for sheaf theory? Okay, and so that's what we're going to discuss for the rest of the talk. Okay, so just to emphasize, maybe to beat the dead horse, is that sheaf theory teaches us to think locally in position space, and microlocal sheaf theory will teach us to think microlocally, both in position and momentum variables, in other words, in phase space. Okay, so the first task is to take some of the algebraic analysis we've heard about, like we heard in Andrea's talk about characteristic variety, to take this notion and see what does it look like in the world of sheaves. Okay, so I'd like to do that. Could I ask, could you remind me, do I go till quarter of or till the hour? To quarter to, great, okay. I think we're firmly in the case of too much material. Okay, great. Okay, so this slide and then subsequent slides, I will try to tell you, I don't know, I thought there was a quote of Gelfand also, something along the lines of a definition is worth 1,000 theorems or something like this. This is one of those cases, okay? So I've paraphrased it. I can't technically explain it to you, but this is one of the great definitions in mathematics. Okay, it's certainly been one of the great definitions in the last 30 years of mathematics. And this is Kashiwara and Schapira's notion of singular support. Okay, so this is a transposition of the notion of characteristic variety from the world of D modules into the setting of their solutions, in other words, into the setting of sheaves. Okay, so let me try to explain what's written here, and then we'll do some examples on the next slide. Okay, so the singular support of a sheaf F, okay, or more generally a complex of sheaves, okay, is the smallest closed subset such that any, and here there are some technical words which I'll explain as we go, any vanishing cycles or Morse group calculations of F at any point of the complement of the singular support vanishes. So let me first, to begin to start to unpack this, let me first just remind you that the usual notion of support for a function or a sheaf is you say first the complement is the open where everything looks trivial, where everything is zero, okay? So this is the same idea, okay? So what I've drawn here, just to kind of, as a cartoon, is say the manifold of the real line, okay? And then I've drawn a point Q with a codirection P, okay? I was very happy in, Masaki, in your description of, but you said you were very impressed by Sato's ideas that you should not just have position, but also have a direction. And it's always reassuring to hear the greats talk about directions, not just codirections. Okay, so technically this is a codirection, but I think all humans should probably think of it as a direction. Okay, so I've plotted, over here, I've plotted the cotangent bundle of the real line, which is now R2, say, and here is that point plotted, here's that covector plotted as a point, okay? And what I've drawn in, just kind of cartoonishly, in red, is the potential singular support of some sheaf, okay? And what this is supposed to convey to you is that if you ask any question of the sheaf for any green dot that's not on the red, okay, you will get a completely trivial answer. So let me tell you the specific question that you ask. What you ask is you stand, and this is just, of course, a paraphrase of more technically accurate things. You stand at this point and you ask, is life at this point the same as life in the past? Okay, so the codirection is telling you the future, which direction is the future, and you ask the question, is life here same or different from the past? Okay, and if it's no different, then that point is not in the singular support, and if it's different, that point is in the singular support. Okay, so I wrote the slogan here. So it's the codirection in which F has a jump. In other words, the past and the present are different. Okay? So here's some examples. So I've written 3 basic sheaves, and we can just go through them quickly. I think this is more important than any kind of technical definitions. 3 basic sheaves. Okay, these are constant sheaf on a point A, constant sheaf on, say, a closed interval, and then constant sheaf on a half-open interval, say, extended by 0 to the right. Okay? And I've drawn, under some conventions, which may agree or not with the experts, I've drawn their singular support. Okay? So here what you would do is you would stand at any point, say this point here in the cotangent bundle, and you ask, is life on the base? So this point corresponds to pointing out in this direction. My slides are, I should have drawn more pictures here. And you ask, is life at this point different from life back here? And of course the answer is yes. Life at that point sees the constant sheaf there, and life to the left of it looks trivial. Okay? So that's why these red vertical pointing up covectors are in the singular support. Okay, and so on. Maybe I won't go through all the examples, but in any case, these are, I think if you understand what's going on in these pictures, you're like, I don't know, 4/10 or you're some percentage of the way towards really understanding what this story is all about. Okay? Okay. And you'll notice that all of these pictures, the singular support is closed, that's just by fiat, but it's also conic. Okay? So in this definition, all we really use is the codirection. We just want to know which way is the future. We don't care how fast we're going into the future. Okay? So that's why the singular support is a kind of conic subset. Okay. Right. Okay, so here's the fundamental theorem that was proved first in the algebraic analysis setting, but then was proved by Kashiwara Schapira here in the context of sheaves, and that's that the singular support of any sheaf or any complex is involutive or coisotropic. Okay, so it's really an object of symplectic geometry. It satisfies the Heisenberg uncertainty principle. Okay, you're not allowed to prescribe too many of the variables, too many of the position and momenta variables. Okay, so this is just like, I'm going somewhat quickly, but this is just like we heard about in the prior talk. Okay, and if you want to see a concrete example, you choose some constructible sheaves, sheaves that are locally constant on some stratification, and then you'll discover that the singular support must be in the union of the conormal bundles, which is a beautiful example of a Lagrangian inside the cotangent bundle. Okay? Okay, so this theorem, or maybe its avatar in the world of algebraic analysis, really tells you secretly what you're doing is symplectic geometry, not sort of just topology. Okay. Okay, now, I don't know, I should have stole Andrea's little difficulty-o-meter. I don't remember what it was called. Okay, so this is, the talk just gets a little bit more difficult here. Okay, one of the most amazing, okay, I've already advertised one universally important definition. Here's a second, okay? And this one is, I don't know how to tell it to you without saying something technical, but I'll do some examples after. Kashiwara and Schapira introduced the notion of a microlocal sheaf. Okay, so from one point of view, it's the most natural thing you could do, okay? So once you have a notion of support, so to every object in your category, you have some red subset of the cotangent bundle, then you can start to localize your theory on the cotangent bundle in a kind of completely formal way. You can say, if I have a small open in the cotangent bundle, I'm happy to quotient anything that has no singular support there. Okay, so this is just a kind of a formal idea that once you have this notion of singular support, your theory lives over the cotangent bundle. And so what Kashiwara and Schapira do is they introduce this kind of definition, which has a lot of words in it, but they roughly say, take any open okay, in the cotangent bundle, and let's just look at all sheaves and quotient out by those sheaves that are invisible to that open, okay? And then you have to sheafify it, as we'll discuss in a moment. That's kind of the key. It sounds technical, but that's the key idea, okay? So this definition is, in some sense, if you're a wise mathematician, this is a definition you make almost immediately after you already have the notion of singular support, okay? Okay, so to illustrate the power of this definition, I'd like to tell you about Zorro's microlocal sheaf, okay? So what is Zorro's microlocal sheaf? So what I've drawn for you on the slide, so the slide is R2, okay? And here I've drawn for you a curve in R2 that has two cusps, okay? So this curve has two cusps, and I want to think about this curve with its two cusps as being some constructible subset on which I want to study constructible sheaves, okay? Now, if we're symplectic geometers and we're interested in conormals, we notice that if we take, say, the positive conormal to this curve, so all of, say, the unit covectors that point normal to this curve and positively, we in fact get a smooth Legendrian at infinity of the cotangent bundle. Okay, so one of the remarkable properties of Zorro's curve is that if you include the codirections, it smooths it out. Okay, so if you just think about this curve in terms of position, it's singular, but if you think about it in terms of position and momentum, in other words, it's normal directions, it becomes smooth, okay? So, not surprisingly, whatever a microlocal sheaf is, along a smooth subset like this, well, Kashiwara and Schapira prove that it looks like a theory of locally constant sheaves. Okay, so if you have this kind of smooth object, then there's going to be essentially one rank 1 microlocal sheaf along it. But according to the definition, how do we access this? Well, what we do is we cut it up into local pieces, and on each local piece, we need to tell you a sheaf downstairs such that that sheaf represents the microlocal sheaf in the quotient on the prior slide. Okay? And one of the remarkable properties of Zorro's curve is that there is no global sheaf that represents this microlocal sheaf. Okay, so this is the first moment where you've really left the reservation. Okay? You're really not doing sheaf theory anymore. The object you're writing down in red up here is not represented by any kind of global sheaf. Okay? It's locally represented by these kind of blue sheaves I've kind of cartoonishly drawn for you. Okay? Drawn some support, but they don't glue together in any way to form a global sheaf. Okay, so this is kind of, for me, this is kind of the first moment where you really see there are objects out there that, Masaki talks about creating. You've just created new mathematics. Okay, this object didn't exist in any sense as a global object without this definition. Okay, so whatever a microlocal sheaf is, it's something that's really an object of symplectic geometry and accessible by sheaves, but certainly, I don't know, there's some quote that Deline said something like, a perverse sheaf is neither a sheaf nor is it perverse. Okay, so a microlocal sheaf, it's microlocal, but it's definitely not a sheaf. It's some other kind of beast of mathematics, and we'll see soon. Okay, so I'm running short on time, so I will kind of go more quickly. Let me mention a couple of the kind of fundamental stepping stones that convince you you're really doing something new and amazing. Okay? So one thing you can ask is, once you've freed yourself from the zero section, you can ask, suppose I have the complements of zero sections and they're isomorphic. Is my theory the same independently of how I see those complements as complements to zero sections? And here I've drawn the kind of famous example of projective duality as a case if you take cotangent bundles and remove cotangent bundles of projective spaces, dual projective spaces, and you remove their zero sections, you get isomorphic spaces, and curves like this in one model look like curves like this in the other model. Okay? And Kashiwara and Schapira proved that indeed their theory of microlocal sheaves are invariant under contact transformations. So their definition has truly liberated us from thinking about the zero section. We're really now like off in a new world doing symplectic geometry, not just sheaf theory on the zero section. Okay, so that's kind of first stepping stone. I think maybe I'll skip this slide in the name of time. Well, okay, I know, I can't resist. So this is a kind of more recent result of Kashiwara and Schapira, Kashiwara and Guillermo, which says, maybe even more remarkably, that the theory of sheaves itself is also approachable with symplectic tools. It says that, in fact, if you look at an isotopy at infinity of the cotangent bundle, you can actually move sheaves themselves with respect to that isotopy. Okay? So I won't go through this, but I'll just say one of my favorite examples is that all of the Hecke operators of geometric representation theory are all basically built from this theorem and this picture. Okay, so this is a kind of beautiful picture in mathematics, but I think I'll continue past it. Okay, so now I've really come to the last part of the talk, which is to say less maybe about Masaki's work and more about how these ideas have really taken off in new and amazing directions. He really created a whole new world, not just kind of downstream of where his work is, but kind of all in all sorts of different subjects. Okay, so we're really now going to think like symplectic geometers. We think of cotangent bundles as symplectic manifolds. And I want to just mention as a first example, so I'm going to go through maybe about 5 slides in 5 minutes, so just bear with me and then we'll all be able to go get some fresh air. I'm going to go through about 5 slides in 5 minutes, mentioning sort of where Masaki's ideas have led. So the first thing I'd like to mention is just kind of in a completely different part of mathematics, Fukaya is defining his Fukaya categories, which are a kind of homotopical organization of Lagrangian intersection theory, of Floer theory. And it's known now, after work of myself and Eric Zaslow, and then recent work of Ganatra Pardinchenda that really proved very powerful locality theorems for Fukaya categories, that the theory of microlocal sheaves and Fukaya categories are the same subject. Okay. So a kind of amazing thing, I don't know that Masaki and Kenji Fukaya are talking to each other, but here are 2 Japanese mathematicians who are revolutionizing the world, and it turns out the revolutions are actually, parallel revolutions. So it's kind of one kind of amazing development. So whatever I've sort of, microlocal sheaves look like a technical idea, but it's really something extraordinarily natural geometrically. Okay. Okay, so in the name of time, I'll just keep moving. Okay, and now we're going to go even farther away. Okay, so in a galaxy far, far away, in fact, on the other side of mirror symmetry, where we care about algebraic geometry, say not symplectic geometry, Orinkin and Gatesgory introduced their own notion of singular support of a coherent sheaf on a singular algebraic variety. Okay, so this is a kind of different setting, completely different setting. We're not on a manifold, we're on a singular variety, and our sheaves are not topological sheaves, but coherent sheaves. But there's a parallel here that is certainly, they're certainly inspired by Kashiwara and Schapira. The parallel is whatever Kashiwara and Schapira's singular support is, it measures how much you're not locally constant, how difficult it is to propagate solutions. And Orinkin-Gatesgory's singular support, building on work of Eisenbud and others in algebra and algebraic geometry, measures how far you are from being a perfect complex, essentially a complex of vector bundles. So both of them are kind of measuring how far you are from being a smooth object, but in completely different ways. Okay? I don't think this would have been possible in finite time without this, even though the mathematics is all inspired by Kashiwara and Schapira, but it's a kind of completely different setting, I think, which really illustrates the power of what they brought to us. Okay, so this is a very dense slide. I have about just a few more slides. So I don't think I'll say very much about this, except to say that it turns out that Kashiwara and Schapira's notion and Orinkin-Gatesgory's notion are actually part of a hierarchy that's important in topological field theory, and related in very interesting ways. Okay, so I'm just paraphrasing what's written there. Okay, so it's interesting how mathematics works. I'll just mention somehow the most basic of all of the business on this slide, the most basic business, is that there is a notion of singular support of a Borel-Moore homology class. Okay, and somehow this is kind of formalized later than much more sophisticated things. But anyway, I hope this conveys to you that the notion of singular support now is understood to be something that's a kind of universal aspect of sheaf theory, whether your sheaves are valued in vector spaces or they're coherent sheaves or whatnot. Okay? And I apologize for going quickly because I'm just out of time. So let me just mention a couple more things and then I'll quit. Okay, so I think I'll just probably skip through. Yeah, maybe all right. At the risk of kind of missing the whole punchline, I'll skip through. I had a bunch of talks about the geometric Langlands program, which I will completely skip and just go to the last slide. Okay, so I'll just say that the notion of singular support kind of led to the resolution of the geometric Langlands program, and I think there's no way it would have reached the state it reached without Masaki's inspiration. Okay, but this is a final slide, and I want to just, advertise a problem for you. Okay, so we talked to students on Monday, but I think this is a problem also for the most senior interested researchers. Okay, so Kashiwara and Schapira's notion of singular support, and say the equivalence of microlocal sheaves with Fukaya categories makes it unequivocally clear that you're doing symplectic geometry when you're studying these notions. Okay, it's inescapable you're doing symplectic geometry. Beilinson recently extended the notion of singular support to constructible sheaves on varieties in finite characteristic. And one of the amazing things he proved was that the singular support is always less than or equal to half-dimensional, but it can truly be less than half-dimensional. And in fact, it needn't even be isotropic. So it's somehow not an object of symplectic geometry as we usually understand it. And it all emanates from the fact that in characteristic P, the fundamental theorem of calculus fails. So our understanding of the relationship between momentum and position breaks down. Okay? Anyway, so I'd like to just end with this question, which, unless there's been recent developments, I know that Sasha Beilinson and I have discussed this very much, and neither of us, I think, has a clear answer to it, is what is the notion of microlocal sheaves here? And what kind of geometry is this? Okay, so here we're really doing something that's not captured by symplectic geometry. So the question is, what is it captured by? Okay, so anyway, I just would conclude by saying, yes, singular support has not only solved many problems, but provided many new problems as well. So thank you very much. I apologize for going over, and congratulations, Masaki.
Thank you very much, David. The floor is open for questions or comments from the audience.
I mean, that notion of singular support you just presented, it feels very much like the wavefront set a la Hermann, except that
yes.
One sort of measures the failure from being a smooth function rather than failure from being constant.
Yes.
So is there...
Yeah, I mean, I'm laughing because I shared my slides with David Ben-Zvi, and his comment was, you don't say the word wavefront set anywhere. So, of course, the first question is, yes, I mean, the notion of singular support is a transposition. I mean, if you understand that algebraic analysis in the hands of Sato, Kashiwara, and Kawai understood the characteristic variety of a D-module, and they're modeling what happens to solutions of differential equations, and our sheaves are just the sheaves of solutions, all of these notions match up. So under Riemann-Hilbert, the characteristic variety matches the singular support under the Riemann-Hilbert correspondence, which also match, if you speak then of the sections of the sheaf as as wavefronts, then solutions are, it's the same business.
Any further questions or comments? That does not seem to be the case, so let's thank David and all the speakers of the day.